Good morning. Welcome to the Quantum Inspire course. Welcome to everyone. We will start with some simple examples of programming on the Quantum Inspire platform. Later, we do some more advanced examples, and we'll take you through the whole thing hand by hand. Today, we will have some short introduction. Then we work through the pre-workshop assignment we send around. So create your Quantum Inspire account and use Quantum Inspire on the web portal to create a bell state using the CQASM language on the QX emulator that's available in Quantum Inspire. And we'll take you step by step to creating the 4 different bell states on Quantum Inspire, which is a very simple example of programming on a quantum computer. Then after that, we're getting started with the Quantum Inspire software development kit, which is a little bit more advanced, and where we also start first with creating and visualizing quantum circuits and bell pairs using the Quantum Inspire software development kit and programming in Qiskit. After that, we do some more advanced examples using the software development kit. We will end with a presentation demonstrating the very advanced use of Quantum Inspire, and after that, we'll do the closing. So now back to the introduction. So this is the course outline of the course you followed. There was 4 weeks of courses with an introduction to the Quantum Inspire platform and the hardware and the simulator platforms and quantum compilers. The second week was more about applications of quantum computers and the quantum advantage and some examples of quantum computing application and quantum algorithms. Week 3 was about the CQASM language, quantum programming language that is available on Quantum Inspire. So an introduction, some applications where you could see a few examples. And the last week was more about installing the Quantum Inspire software development kit and using programs like Qiskit or PennyLane, Project Q. So I hope you followed all of this because I repeat a few things before we start into the exercises. One of the things is, of course, what is really important and a really difference between a quantum computer and a normal computer. 2 basic things, which is superposition principle and entanglement. Entanglement we go to later when we go through the bell states. But the superposition principle is actually a classical bit is clearly 0 or 1. And a quantum bit can be a linear combinations of 0 and 1s, for 1 bit at least. And the parameters, the modulus squared of the parameters give the probabilities that a qubit is in a certain state. For more qubits, of course, this will expand. So in the second example, in the middle, is about 2 qubits that can be in 4 different states. And again, with the parameters that indicate the probability that is in one of the states. And you can continue that with an infinite number of a large number of qubits, and then you get a linear combination of those. This was all done in the course, so I hope you remember. And the second thing is the quantum gates, also important. So classical gates, like in this case C0, are not reversible. So they give an answer that is not directly traced back to the input. With quantum gates, they're fully unitary operators, so you can have a fully reversible gate. In this case, a C0 gate, where the first bit is actually the control bit, which determines whether the second bit will flip. And this is all in the Z basis, if you want. So those are, I think, the 2 important aspects of quantum computing. The last one, the bell state, we will go to later. You are able to use Quantum Inspire and log in, and make an account, log in, and go to the web editor, actually, which you see an example here with different examples in here and using the CQASM language. So that's all good. We can go quickly to the creation of bell states. Yeah, this is all about entanglement, one of the last major aspects of a quantum computer. And in this case, we create a bell state, which is a maximally entangled 2 qubit state. Of course, always the overall probability of the qubits in one of the states is always 1 in total. And you can actually create 4 bell states. You see on the right, the phi plus and minus and the psi plus and minus, which is a different combination of the different states of the qubits, as you can see. And I put a link on the top to Wikipedia where you can read more about the bell states, which is also available in the knowledge base on Quantum Inspire. So you've all seen the polyxgate now. On the right side, you see how you can program this in CQASM. If you start with a qubit in the 0 state in the Z basis, and then you put the X polygate operated on it, you of course get the 1 state with a probability of 1. Last gate we need is the C0 gate, which actually is a controlled NOT, which means that the first, if that operates on 2 qubits, and actually if the first control is the control qubit, and it performs this polyx gate on the target qubit when the control qubit is in 0, in 1, and otherwise not, it stays the same. I will show later how you can program this on Quantum Inspire. This is all again available on the knowledge base in Quantum Inspire. So now, how do we generate these Bell states? Well, the simplest, there are 4 Bell states, as I explained. The simplest one is on the left top corner, where you first put a Hadamard gate as an operator, and secondly a C0 gate, and then you create the phi plus state, which is a linear combination of the 0, 0 and the 1, 1. Of course, you can also create the others, as you can see, the psi plus, the psi minus, and the phi minus, which are different linear combinations. And then you have to use different gates in a different order to get these results. This you can easily program in Quantum Inspire, in CQASM. I will show you an example. As we saw in the poll that all of you succeeded to do this. If you now go to Quantum Inspire again, and as you can see here, as a CQASM example, this is then an example of the phi plus gate, the simplest one. So you can see that you have to first define the registers, the qubit register and the bit register. Bit register is just to store the measurement result. And then you initialize in the Z basis, and then you operate, as you can see, an Hadamard gate on the first qubit, and then a C0 gate on both qubits, and then you measure here, which is, and you put the result in the bit register. And if you run this, you get the result here. As you can see, as expected, it should be equally divided over the 0, 0 and 1, 1 state. It's actually quite simple. You can do also the other ones. I will quickly go through it. So if you you see here the phi minus example, where you first put the X polyx gate, and then the Hadamard gate, and then NOT gate, C0 gate, and then of course you get the result equally divided in 0. No, this is not the right one, of course. I have to show the other result. And equally divided over this one, 0, 0 and 1, 1, which is of course the same. You can go to all the others as well, and you can see that you have to in order to create the psi minus state, you do this one, and in order to create the psi minus, you can do this one, and then the result you can see here, which is then an equally divided over the 0, 1 and 1, 0. So given that you have all succeeded in doing this, we don't have to go deeper into this and go over it again. So back to the presentation. So for references, for a more advanced background on the CQASM language, you can use this link here. And for the Quantum Inspire knowledge base, that's in the Quantum Inspire environment, there's also a link where you can find really a wealth of information, all this, on all these gates, but also on a lot of other things. There's also a link to the evaluation survey, which you can fill out at the end of the course.
So hello, everyone, and thank you, Marco, for the introduction and assignments with CQASM. There are 2 options. You can either just make a copy of this notebook and start executing it. So for example, you can go to File. You can save a copy in the drive and start executing it, or you can also go to File again and download this notebook, download it with the IPyNB extension so that it goes out as a notebook. And you can start it on your local machine, or you can upload it back again on Colab and start using it. So what we will do is, I will show you at least I'll walk you through the challenges. We will solve some challenges here. in the Google Colab notebook. And I also have my Jupyter, locally hosted Jupyter notebook, where I have all the solutions already, which I won't show you now. Let's walk you through it. So if you are ready to start, you can press on reconnect. This will connect you to the Google Colab server. As you can see, mine is still connecting. It's green now, it's connected, shows you the RAM and disk space available. And if you're using it on Colab, it's important that you install these packages. If you already have these packages installed, because they were also shared as a part of the pre-workshop assignment, pre-assignment of the workshop, then you don't need to do this step. But if you're on Colab, you will always need to do this step when you start afresh. So, and sometimes things can go wrong on Colab because Google Colab also keeps upgrading the software versions. Especially I faced some issues with NumPy and Pandas. At the moment, it's installing the necessary packages. You might see some version conflicts, but you can ignore them as the software would work as it's intended to. So you can see it's installing and uninstalling some of the packages. We do see some dependency conflicts, but it would not be a problem. Okay, so this step has been executed. Now it's very important that you go to your runtime tab and choose restart session. This is to ensure that the packages that were uninstalled or installed are fully available in your environment. So you can see it says restarting, and it's, in my case, it's restarted now. And now before I log you into the environment, I'll execute the next cell just to check if all the packages are working fine. So it was able to import NumPy, Pandas, and it was also able to, yeah. So all the packages, they are running fine now. I hope all of you have an account. So you have a registered email address on the Quantum Inspire Cloud. So you can just execute this cell. You can confirm. Login is successful in my case. Here we have defined some basic Python functions. You don't need to worry a lot about them. You can use them as it is. They're essentially to get the raw data after certain experiments are executed on the server and to process them, to convert them in probabilities. So you can feel free to look at the code itself, but it's nothing very, there's not something more quantum about it. So you can, for now, I will just execute them. And since there are no errors, I'm very happy. What we now do is we will first connect to the Quantum Inspire provider. And we can do this by calling the code provider equal to the QI provider. If you remember, when we were importing the cells, from Qiskit Quantum Inspire provider, we imported this functionality QI provider. So I will now call this functionality. And I list what are the available backend names. So you can see we have 3 available backends. The first one is an emulator. We will use the emulator for one of the first exercises. Another one is a semiconducting backend, Spin2+. In this workshop, we will not be executing any examples on the Spin2+, but I request you to explore it on your own. It's a 2-qubit backend. And then we have a superconducting backend, StarMon7, which is something that we will be using a lot in this exercise. It has 7 qubits in total. So let's now declare a backend name StarMon7. So you can see it does not give an error. It's connected. So the first thing when we are working, we are in the early days of quantum programming. So we need to have more information about what our quantum chip looks like. And an important parameter there is what is the connectivity of your chip? What is the topology? So if you want to look at it, you can make the coupling map. If you are on your local system, it is possible that it gives you an error because it requires some dependencies, visualization dependencies like GraphViz. If they are not installed on your system, you might experience issues. That's not a problem. You can look at this link, Quantum Inspire backend slot StarMon7. And with this link, you can, so if I can also walk you through there once. So you see, we have a picture here, which shows you the connectivity of the qubits. And it also shows you the qubit number. So you can see that we have a central qubit, and that's connected to qubits on the periphery. So we have several 2-qubit connections in here. Now, we can also print both the two-way connectivity of the qubits in a list. So I have some Python code there. It shows that qubit 0 and qubit 2 are connected to each other. Qubit 2 and qubit 0 are also connected to each other. That might sound a bit redundant, but that's what it prints because these are, yeah, you can have both way operations. You can also look at the native instructions on the backend. So if you do backend.instructions, it shows you a very large list of all the supported instructions. We will come back to this at a later stage in this workshop. Now many of you, I hope, are connected to the SDK. You are able to use it either locally or on the Colab. I think for the purpose of this exercise, it's easy to get started on Google Colab, but feel free to make a choice. Now what we will do is we will start making some quantum circuits. So Marco already told you about some of the basics of quantum gates. What I will ask you in this exercise is to make some very small 1 and 2 qubit quantum circuits. To get you started, I already have an example. So here I have shown an example of creating a poly X gate. So what you do is you essentially start the name of a quantum circuit at QC_X, and you call the quantum circuit function from Qiskit, and you say that it's a quantum circuit with just 1 qubit, and then you apply the X gate. You can do this by QC_X.X, and then give the qubit index, which is 0, that applies the X gate, and you can visualize it. What I will do is I will comment out this code, this part of the code, and I'll just execute it. And you see it shows me the quantum circuit. We have 1 qubit. It applies a poly X. What I invite you to do is to fill the rest of the Google Colab notebook. So I'll uncomment this part. So please take some time and start to apply a Hadamard gate, a CNOT gate, and a CJET gate, taking inspiration from the example of the poly X. Please also go through rest of the examples, like applying a Hadamard gate, a CNOT, and a CJET gate. Remember that for CNOT and CJET, you will need to define a quantum circuit with 2 qubits. So essentially, instead of saying quantum circuit 1, you would want to do quantum circuit 2. And the hint examples already tell you what symbol to use for a Hadamard. It's a small h. For CNOT, it's a CX, and for CJET, it's just CJET. The complete notebook of this workshop will also be shared with you at the end. And if you are having some issues with packages, like there are conflicting dependencies, or you are simply struck with the installation, I would request you to bear with us, because the whole exercise will not be too much about you testing your knowledge, but more about experiencing the SDK. I will move on to the next steps. So Marco, in his presentation, told you about bell pairs. Here we will again revisit the bell pairs, and we will create them with the help of our SDK, the Quantum Inspire SDK. So there are four bell states which essentially give you a pair of qubits. There are phi plus, phi minus, psi plus, and psi minus. They can also be transformed among each other. Let's say you have created the first bell pair, which is the phi plus state. You can see here, the first one here. If you want to go to if you essentially want to create the phi minus state, what you do is you apply a JET gate on the first qubit. This is one of the ways to do. I think Marco shows you a different quantum circuit arrangement to also do that. You can also follow that approach, or you can also follow this approach. They are both equivalent and should get you the bell pair. So essentially, you apply first a JET gate on the first qubit 0. And mathematically, it's denoted in this manner. It applies a JET gate with an identity on the second one. So the gate only applies to the first qubit, 0 qubit in this case, and the qubit 1 in this case. When you apply the JET gate, if it encounters the state 0, it leaves it unchanged. If it encounters state 1, it converts it to -1. So you can see if you apply a JET gate to the first qubit in this manner, you end up with the phi minus state. Similarly, you can create a psi plus state from the phi plus state using the X gate. And you can also create the psi minus state using a sequential application of X and the JET gate. So you first apply a X gate followed by a JET gate, and it will get you psi minus. You can take your time to go through the derivation of these, but trust me, they work. I have also printed here a handy table which describes the transformation among the Bell states. It essentially boils down to applying a jet gate or, for example, an X gate or X and jet gates to the first qubit 0, and you can do the transformations among each other. It's handy to keep it in. Now that you have gone through the creation of Bell pairs, I have a challenge for you. What I want you to do, or what I request you to do, is to write a function which creates the Bell circuit. So here's some skeleton of the function. It should ask the user for which state they want to prepare. By default, if you don't provide an input, it would default to the 5+ state. It also asks you the indices of the qubit pair. By default, it's qubit 0 and qubit 3. Why we take those qubits? Well, what you can see here, you can also work with other qubit pairs, but if you want to create a 2-qubit gate, normally you would want to work with qubits that are directly connected to each other. That might sound a bit cumbersome, but we also have a way around that will come subsequently in the exercise. For now, we are working with these 2 qubits. As default, you are free to define any other pair of qubits and experiment with it. Once you have done that, we have a definition of what the valid quantum states are in this case. So this essentially validates if you have given the correct argument to your function. So if you give it something like a zeta state, it won't work. It will raise a value error. And then I want you to write the circuit for creating the code for creating a quantum circuit, which essentially creates the 5+ state. Remember what the 5+ state is? It's essentially a combination of a superposition of the 0, 0 and 1, 1 state. And you already know how to create this, create a 5+ state from the talk from Marco. I can give you some hints. You would want to use the quantum circuit method that you used earlier in the previous exercise, and you want to initiate it with 7 qubits and 2 classical bits. Then you want to apply a head-mod on qubit 0, followed by a CNOT gate on qubit 0 as control and qubit 1 as target. Once you have done that, you can go through the next steps where you essentially apply a jet gate to qubit 0, or you apply a X gate to qubit 0, or a X and jet gate to qubit 0, and at the end you return the quantum circuit. So you are experiencing this issue with NumPy, and the hack here is to essentially restart the session. So you go to the runtime tab at top and restart your session. This issue essentially occurs because Colab already has a preset of certain commands, certain packages, and there's essentially conflict between different dependencies. You can see I filled in some of the suggested solution. So the first challenge was to create a quantum circuit with 7 qubits and 2 classical bits. So essentially you call the quantum circuit function with functionality with 7 qubits and 2 classical bits. Then you apply a head-mod on qubit 0. So that's essentially qc.h and qubit, the index of the qubit. And then you apply a CNOT on qubit 0 and qubit 1. If the user supplies a phi- state, then you can apply a jet gate on qubit 0. If it's psi plus, you apply an X gate. And if psi minus, you apply X followed by a jet gate. So that's the solution. Now what we can do is we can connect to the emulator backend. It's not necessarily, you can also execute it on Starman 7, but I wanted to show you an example also with the emulator backend. So we are connected. And here I have some code. What it will do is it will run a for loop. It will go to each step. It will create it will essentially create the Bell circuit. So here I request you to fill in, essentially call this function that you have created. And once you have done that, it will, a rest of the code is provided for you to make the histogram. You can run it. It will display all the quantum circuits and the results as it gets back from the backend. Here it's important to make note of these code blocks so that after qc.measure instructions, we have job equal to backend.run. This is how you send the job to the particular backend. Then you can query the results back and you can get the counts from to make the histogram. So keep this in mind, because in subsequent challenges, I'll ask you to fill these parts of code in. And yeah, it's important that the function that you have created will create the quantum circuit. You can display it, but it's not going to measure the qubits for you. You have to also provide it with measure instructions. So what we can do here is we'll essentially say create Bell circuit. We give it functions like state and qubit 0, qubit 1. So it will create, so it has created the first one, the first pair. And I hope it has sent the job on the Inspire backend. Let me check. I see a job has been received. You can look the CQASM behind it. So it applies the head mod on the first qubit, it applies a CNOT between qubit pairs, and then measures both of them, also displays it. You are familiar with this environment, and you can see the results. It's roughly 50-50. We can also go back to our Colab. It's still executing. Now it has created the psi minus state as well, and it gives you back the histogram. So in STARMan7 backend, you would see different populations. So there are also some unwanted states that might get populated, and that's what working on real hardware is like. You have some errors. And you might notice that when you are using the emulator, the bit strings on the x-axis, they are a little bit differently formulated. This is because of the way emulator returns the output. But if you go to the Quantum Inspire web portal, not this one here, then you can see that it shows you. So since you are using qubits 0 and 3, so this is your qubit 0, you read it from your right, and then qubit 1, 2, 3. So this is the 1, 1 state, and then you have the 0, 0 state, which is difficult to read because they are all zeros. So it's important to keep in mind that when you are using the emulator, the way it returns the results is slightly different. It's not wrong, but slightly different, and sometimes it can be a bit confusing. So now that we have written on functions to create essentially the Bell pairs, let's let's revisit the coupling map of STARMan7. So what I'm going to do here is so I've just generated the coupling map of STARMan7. So you can copy the codes from a couple of blocks above, where you provide the backend name to be STARMan7. You get the backend from the provider, and then you draw the coupling map. It's a very handy tool to visualize the circuits. If not, you can also always refer to our website. Now what we are going to see is, what if we create a state where we use qubits that are not directly connected? And in our case, it would be qubit 0 and qubit 5. So what I'm going to do is, I'm going to declare my qubit 0 as 0, qubit 1 as qubit index 5. I'm going to create again a 5 plus state. And what I'm going to ask you is to repeat the exercise, but not for all the states, but essentially write the function, call the function again to create the Bell pair. You can display it and measure the qubit and send the job. So essentially you need to take this block of code and you have to adopt it here. And the experiment failed. Can you take a moment to reflect as to why it would fail? And that's not an error. This is essentially intended. So what we were trying to do is we were trying to execute a 2-qubit operation on qubits that are not directly connected. This confuses the system because there's no way to execute this circuit directly, and that's why it gives you an error. Now what I'm going to demonstrate to you is, if we repeat this experiment now. So essentially what we do is, instead of qubits 0 and 5, we recreate the state 5 plus using qubits 0 and 3. If you look at the coupling map, 0 and 3 are connected qubits, they are well connected. So we recreate this experiment. We again create a Bell circuit. We can display it, measure it, send the job to the backend, get the results and get the counts. So let's say we execute this. So you can see there's a head mod applied on qubit 0, a CNOT between qubits 0 and qubit 3. And now it's trying to get the results back. So the job is already sent. Maybe I can look in my projects environment on Quantum Inspire Cloud. It's already done. And I have some results here. So it was successfully submitted, right? We can get the counts. We can also plot the results here. So you can see there is there are some unwanted states. So 0, 1, and 1, 0 states are also populated. This is due to errors on real quantum hardware, which is something that we try to minimize in general. So now you have gotten a good feeling of using the Starman 7 backend via the Quantum Spire SDK. You can create bell pairs. You know that if you want to create a quantum circuit and perform a 2-qubit gate operation, you want to do it with qubits that are directly connected to each other, but that can be quite cumbersome, right? To remember it and to, like, essentially if you're writing a large program, and I hope that you do start writing large programs, to remember the qubit connectivity. But there's a way around it. So let's look again at the qubit connectivity here. I think by now this diagram is etched in your memory. What we are now going to do is we are going to create a quantum circuit. This time we do it just with 2 qubits. So instead of calling quantum circuit 7, 2, we want to do quantum circuit 2, 2. We don't specify the qubit indices specifically, but we create our bell pair. You can use the function that we created, but it might require some adaptation. So I've just requested to write the 5+ state yourself. So you apply the head mod on the first qubit, you apply a CNOT gate on qubit 0 and qubit 1. You measure the qubits and you visualize the circuit. So we want to create a quantum circuit with just 2 qubits now. To do that, we just write the command quantum circuit 2, 2. We apply a head mod on the first qubit, so qc.h0, qc.cx 0, 1, and then we measure the qubits. Okay, so now we have created a quantum circuit with 2 qubits. We apply a head mod on the first one. We apply a CNOT between the qubits, and we essentially perform the measure operations on both of the qubits. But how will the program know which qubit pairs are to be used? We are not providing it with, you would use qubit 0 and qubit 3. So let's look at what is the connectivity here. So the connected components are 0 is connected to 2, 0 is connected to 3, 1 is connected to 3. You can see different qubit pairs that are connected. What we can do is, if we don't specify the qubit connectivity or we don't tell which qubit pair to use, it will just start with the first one. So it will just connect the qubit pair qubits 0 and qubit 2 and so on. But we also have the freedom to look at which qubit pair is best. And for that, we can look at the performance page. So if you click on this link, I already have it open here for me. So you can see we have the Starman 7 performance metrics. You can look at the T1s, the relaxation time of the qubits. You can also look at 2-qubit gate performances. Here you see qubit 0 and qubit 2, they give you 98.2% fidelity for 2-qubit randomized benchmarking. Some qubit 1 and qubit 3 seems to be the best now. And this is a dynamic parameter, so it depends on the state of the system, and we keep updating this page. So based on this, you can start to specify which qubit pairs to use. What you can also do is you can scrape this website with the help of some Python commands, and you can get the table. So here you don't need to write this code. You can study this later on. You can also improve it if you want. But we are using some basic Python libraries like Beautiful Soup and Request to just see it has now generated a table with the qubit pairs and the relevant 2-qubit fidelities. And what we can do is we can use this table to create our priority list. So here again some Python code. It says that qubit 1 and qubit 3, this pair 1 and 3 is the best pair. It has 99% performance. And then comes qubit 0 and 3, 3 and 6, 0 and 2. So now when you transpile the circuit and you tell Qiskit that, hey Qiskit, this is my priority list. If you are going to use 2 qubits, use this initial layout. So Qiskit transpile functions allows you to use the initial layout, provide an initial layout. Here we say that use the qubit priority list and look at the first 2 qubits, because the number of qubits in our circuit is just 2, but you can also scale this approach for more number of qubits. So let's transpile this circuit and you can visualize it. So you can say qc underscore transpiled dot draw, give it the button to draw upon. So you see it has again generated your HADMART, and this time it's using qubit indices 1 and 3. Why 1 and 3? Because in our priority list, which we learned from the scraping the performance metrics website, is that qubit pair 1 and 3 has the best performance for 2 qubit gates. Great. We also see that the transpiler has added the rest of the qubits by itself. And these are referenced as ancilla qubits since they are not being used in the algorithm. What I ask you to do is to essentially send this job to the Starmon backend. And for that, what you would need is you need the code to send the job. You have already gone through it. I can also give you a small hint. So you need to specify the backend name, and then you need to use this code that you essentially define the job where you send the circuit, you query the results back, and you print it. So we have defined the number of shots. What I want you to is to send this job to the backend. Backend is Starmon 7. We have already defined it, but be careful not to send the quantum circuit, but the transpiled quantum circuit. So please take a moment to fill in this code for yourself and change the quantum circuit parameter here to QC underscore transpiled so that you are sending the right circuit. If you are seeing that the list URL needs to get a certificate update, that's true. So for now, you can set the option to verify equal to false, which is what I have also done in my command. But this is something that that will be updated at a later stage. And if you send this job to the QX emulator backend, you'll get nearly 50-50 population of the states. You can see there's some error. You can also try increasing the number of shots. Instead of 1024 shots, the maximum shots that you can give is 19,192. The job will take more time to execute, but you can feel free to experiment with 2048 or 4096 shots. You can see my examples are also running, and I got skewed distribution. I got 64% and 36%. You can also, you also don't have to use the first 2 qubits. You can also say from the priority list, use a different set. So for example, so now it's between qubits 0 and 3 instead of 1 and 3. So you can play around with this information. So slightly different distribution of 58% and 42%. Can try increasing the number of shots. So we can, let's say, try with 8,000 shots. It will take longer to execute. Yeah, different result. What I would ask you is to scroll all the way up to section 1.2. So that's log into the QI Cloud platform. So once you're here, please execute this cell so that we can make sure that you are logged into our Quantum Spire Cloud platform. My login is successful. I hope yours will be too. Let's try importing the packages again. Okay, still works. Utility functions still work. look at the provider, good. And, providing *107, everything. So we don't need to execute all the cells. We don't need to also go through the exercises again because they're still fresh in the memory. What we can go is we can let me get back to the right cell. So we were exploring creation of bell pairs using Qiskit transpiler. I showed you a way to create a quantum circuit without specifying explicitly the indices of the qubits. So you created a quantum circuit with 2 qubits and 2 classical bits. You applied a HADMART, a CNOT gate, measured them, drew them, visualized them, and then we looked at what is the list of the connected components. And what Qiskit transpiler does, it essentially it essentially goes through the first qubit pair in this connectivity list and so on. So if we don't specify it, it just goes by the default layout, but we have a performance metrics website where the 2 qubit performances are listed. So we scrape that. There's no need to scrape it. You can also just manually create this qubit priority list. So here we created a Python list where we have a qubit pairs. So qubit 1 and qubit 3, qubit 0 and qubit 3, qubit 3 and qubit 6, qubit 0 and qubit 2 that you can read out also from here. There are better qubits based on the latest calibration data to execute a 2 qubit gate. Then we transpiled it using the Qiskit transpile function, which we had imported all the way up from Qiskit package. We transpiled it, we said it, do it with our backend, which is *107. We also provided it an initial layout, and here I told it to use entries 2 and 4, which is qubit 0 and qubit 3. You can also say it to use entries 0 and 1, qubit 1 and 3, and so on. Then we visualize the circuit. So let's, the priority list should still be in the memory. Let's see if the performance parameter should not have changed. Okay, we are also able to visualize it again. And then we selected a backend name, *107, connected it with the provider. We specified the number of shots and we sent the job to the backend and we got the results back. Let's execute it once more. So it's executing. You can see it's querying the results back. And I can already see under my projects environment that the new circuit was created. It's still running. And now it has the results. And I think more users are using it. So I experience a slight lag, which is not normal, but I'm very happy that you're using it. So we see a slightly skewed distribution. Ideally, it should be 50-50, but we have some errors. We can also visualize, we can also make the plots here. So it says that we created a plot using qubits 0 and 3 with *107 backend. And now we'll go to the next step where we will also tell Qiskit, hey, what are my native gate sets? Because it's a new hardware, different kinds of gates may or may not be supported. And what you sometimes want is to make, so when you make a circuit in using Qiskit, when you transpile it, so for example, here's a visualization of the circuit that I transpiled. It has a HADMART and a CNOT. But if you look at the operational specifics of *107 backend that's available via a link here in our knowledge base, you will see that the only native 2 qubit gate is a CZ gate. So behind the scenes, without the user even noticing, there is another transpilation step on the Quantum Inspire platform where this CZ is further decomposed with the help in 2 CNOT gates. It's not a big problem, but if you want to create circuits that uses the native gate sets, it could be for optimization purposes. You might want to send your circuits that way. And what I found practically useful is if you're a beginner or even if you're an advanced user, but you would like to leverage AI to generate your quantum circuits, large language models like Anthropic's Cloud or ChatGPT. If you give them information about qubit priority list, the coupling map, and the native gate sets, they give you more useful code. This was my practical experience. So that in that sense also it's useful that you know about that you know a way to provide the native gate sets. So here's a list that I have compiled of *107 basis gate sets for you. And what I ask you to do now is once again define perform a Bell state preparation. So I have already defined 2 qubit indices for you. And so it could be 0, 1, but these are like sort of dummy indices at the moment. We are not supplying real indices. So what I ask you to do is to create a quantum circuit. You can work with me. You call the quantum circuit function. You say prepare it with 2 qubits and give it 2 classical bits. And then you apply a head mod on qubit 0. So you say qc dot h qubit 0. And then you say quantum circuit dot c naught qubit 0, 1. And of course, you have to measure them. So what you do is qc dot measure qubit 0 is measured in classical bit 0, and qc dot measure qubit 1 in classical bit 1. And you can visualize it. You can say qc dot draw, use the PL backend. Let's see. So as usual, not something very surprising. And what we can now do is we have already defined the qubit priority list. So we will transpile this circuit. So we'll create a new circuit called QC transpiled, which will use the transpile function, take the circuit as the input, the backend, and the initial layout. So here we are using the first 2 qubits. That would be qubit pair 1 and 3, if I remember correctly. And we also say, hey, these are my basis gates. So make your circuit using these gates. So we now transpile the circuit, successful, and then we visualize it. So you now see, so what was our initial circuit like? It was like a head mod with a C naught. Now we have rotation pi, Ry, Rx gate, rotation by pi by 2 and pi for both qubit pairs. And then there is a CZ gate, and then there are again rotations that are involved, and we have measure statements. So it has essentially decomposed the circuit using the native gate sets that we have available on our backend. So what we can do is we can send this job to the backend. For that, you can copy the code. From here, we have already defined the number of shots and everything. So you can take this, you can work with me. So you essentially have to send the job to the backend. So you are sending the QC underscore transpile. You don't want to send the original circuit because that will, what would be the point of that? So we can describe more shots. We can also say, okay, get the results, and we can also get counts. For that, we can say counts from the results. Please get the counts. Yes. So here we say get counts. Okay, so I have now sent the job to Quantum Spire backend. I can look under my projects directory if it has created. There's a new one. It's running now. So you can see instead of having the head mod operation listed here, we have now sent it in terms of native gate sets. So there are these Rx and Ry rotations and the CZ rotation, and the result is done. And we get, again, a slightly skewed distribution. We have lost some of the qubits to states that should not have been populated due to, this could be due to errors, could also be due to, several errors on a real hardware. So you can also visualize the results here. So what I have shown you, to summarize, is you can create quantum circuits. You can create with the help of basic gates. You can provide specific qubits. Using the quantum circuit function, you can provide which specific qubits to involve in your operation. But you don't necessarily have to remember that. You can also use the transpile function by providing a qubit priority list. That qubit priority list can be constructed by leveraging the information that we have on the performance of single and 2 qubit gates. Once you have done that, we also showed you a way to use the basis gates of the Starman 7 backend, and that has some practical benefits. And now we are able to, and you are able to use the Starman 7 backend using the Quantum Spire SDK. Marco showed you a way to use it with the with CQASM using the web version, the web app that we have. And now I will conduct a small experiment, which will essentially estimate the relaxation time T1 of a qubit. Here you don't necessarily have to follow any exercises. You can just follow along with me. We will use a functionality called mid-circuit measurements. From the name, it's kind of evident that we will do measurements. which are done in between of the circuit instead of doing all the measurements at the end. And what is T1? You might ask, you might already know about it. So T1 essentially estimates the relaxation time of a qubit. Let's say you prepare a qubit in state 1, and you want to know for how long does this qubit stay in the state 1. So in this measurement experiment, we prepare the qubit, and then at regular intervals, we keep looking if the qubit is still in state 1 or if it's decaying. And here the technique of using mid-circuit measurements, which is a key functionality, and it's also very important for quantum error correction experiments, will be used. So we can define a qubit number. Let's say we do it for qubit number 1. We have defined certain parameters, which are total number of points, what's the total time that we conduct. You don't have to change these parameters necessarily. And then based on the central controller of the electronics of this instrument, we have set a 20 nanosecond cycle time. And then we set some more parameters. We define a quantum circuit natively with 7 qubits. We essentially prepare, we apply an X rotation on the qubit. So when you do X rotation, it essentially flips it from 0 to 1. And then we measure this qubit, and we include several mid-circuit measurement steps in between. So if you execute this cell and you draw the circuit, what you would notice is that here we have all the qubits, qubit 1 to 6, then there are classical bit registers. You apply the X gate, it should go in number 1, and then you keep measuring it. Measure it here. You set a certain time delay, and then you keep measuring, set a delay, keep measuring. So what you are trying to see that, hey, qubit, you should be in state 1. And then, are you still 1? Are you still 1? Are you still 1? You keep asking it. Eventually, the qubit gives up and says, nah, I'm finally 0. So what you do is you send this, let's give it a slightly larger number of slots. If you have seen this, and what we want to do is we have set memory equal to true because we want to also return the raw data. So we'll send this to our backend. This will be a slightly longer job. Let's see. Look at the circuit. See, it's X, and then we essentially what we do is that we keep measuring it in different bits and keep asking, hey, what's your state? What's your status? It's a very interesting way to look at the data. You can also inspect the raw data. Look at the length. It should match the number of shots that we have fired. And for each one should be like, how many points you are measuring. So we provided the number of points to be 31. So we are just doing a sanity check on the dimensions. Now, in the beginning of the exercise, if you scroll up, you don't have to, but we define some functionalities about getting the raw data counts, creating probabilities from the raw data. So we are going to use that. Execute these 2 cells. There's some more information about these utility functions. And then we compute the probability of finding the state in state 1, finding the qubit in state 1. So what we have done here is we are computing the probability, and we perform an exponential fit, and we get overall T1 value. Here it's 10.07 microsecond. I think this is a little bit suppressed due to some reasons. And these systems are very, very sensitive to different regions, so to different things. So you might want to check the system performance parameters. This was done a few hours ago. You can see when the last calibration was performed, and you can see the T1 time for qubit 1 was 12.4 microseconds. So it had deteriorated slightly in our measurement, but that's not a big problem. So that was all from my side that I wanted to show you. All of these exercises that were prepared, I didn't prepare all of them originally. I had a lot of help from our colleague Marios. Then I will request my colleague Marios to join in and show you some advanced scientific applications of using that were achieved using Quantum Inspire platform in Professor Leo DiCarlo's lab. Marios, off to you.
All right. Well, thank you for making it to the end of this workshop. So I'm Marios Amniotis. I'm a PhD student in the DiCarlo lab in QTech, and we are working with superconducting qubits. And I guess this is a bit more of an advanced and deep dive into how we are using the quantum processors in research. So You might find some topics that I cover here a bit more difficult, but feel free to ask questions. Yeah, let's get started then. In Quantum Inspire platform, back in 2020, we first released the Starmon 5 processor. It was also released at the same time with the Spin2 system. Now this year, Starmon 5 was officially retired, and then we upgraded it with Starmon 7, which is 7 qubits. And here I'm also putting to you a link where you can go to our GitHub repository and you can get started with using it. So part one, we're first going to see how we can use a processor as a computational tool for quantum simulations. And what I want to talk about is a very nice example from physics. So imagine that you have a solid, and imagine that you also take a section of this solid. So this two-dimensional section, if you go on the microscope and you look at it, then you will see that it is made of a crystal lattice, and the atoms of the solid are vibrating in the fixed positions of this lattice. And what I want to talk about now is that maybe some of you might have followed elementary course on quantum physics or maybe chemistry. If the valence electrons of the atoms that make up a solid, and the valence electrons are basically the electrons at the outermost shell of the atom, if they give a non-zero magnetic moment, then these atoms have a magnetic moment. And in the case that all of these are aligned in the same direction, this is what we call a ferromagnet. And this gives rise also to ferromagnetism. And this is an effect, magnetism is an effect that is basically explained from quantum physics via this mechanism. Now there's some other types of magnets, and one of it is where the spin of its neighboring atom is opposite, and this gives rise to the antiferromagnetism. And how can we simulate such a system using a quantum computer? Here I'm showing to you Starmon 5. Back when Starmon 5 was online, I actually ran the simulations. So that's why I'm using Starmon 5 here, but you can do exactly the same simulations in Starmon 7. So how can we simulate the system? I'm gonna take 2 spins, one that is up and then one that is down, and I'm going to assign to the spin up the state 0 and to the spin down the state 1. And I'm going to say that, okay, I'm going to simulate and map the spin up to qubit 2 of Starmon 5, and then the spin down to qubit 4 of Starmon 5. And notice how those 2 qubits are connected in Starmon 5. How do we formulate this problem? In quantum physics in general, we start with the Schrödinger equation, and this equation governs the dynamics of any closed quantum system. And we have 2 sides to the Schrödinger equation when we talk about solutions. We first have the eigenvalue problem, where we basically solve the Hamiltonian of the system, and we solve for the eigenstates and eigenvalues of that, which means that you get the energies of the Hamiltonian and the states that correspond to these energies. But there's also the general solution of the problem, which is that I have an initial quantum state, and then I'm looking at the evolution at any given time. And this is what I'm going to simulate now. I'm going to simulate the general solution of the Schrödinger equation. And as we already said, we have that the spin up is mapped to the state 0, and the spin down is mapped to the state 1. And this is the Hamiltonian that describes the interaction between two neighboring spins. And the J, in the case of an antiferromagnet, the J needs to be greater than 0. And for a ferromagnet, it would be less than 0. And how do we do that, though? Because now we have a Hamiltonian that if we put in the exponent, it is a sum of operators. And that is not easy to apply as a gate itself. So in order to be able to create an operation that then we can apply to the qubits, I'm going to use a technique that is called trotterization. And basically with trotterization, you can approximate the Hamiltonian in the exponent by breaking it down in this way that is being shown here. This is an approximation, and of course, the higher order of the trotterization that you get, the better the result is, the more accurate, but it comes with a cost that the more you increase the order of the trotterization, the longer your quantum circuit is going to be. And then you're susceptible to noise. And therefore, there's a very fine balance between how much of an order do I need to be able to get accurate results versus, okay, I have to be also careful because if I choose a very big order, then noise is going to corrupt the result. And you can imagine that the exponential that I have here is basically written in this language. So this is the quantum gate expressed as a unitary operation that I'm going to apply to my qubits. Here I'm showing to you the solution to the problem. And I'm showing to you at the time instance of 5.82 nanoseconds when I run the simulation, the circuit on a qubit 2 and qubit 4. And here you see the time evolution of this system of two spins. So you start with qubit 2 being in the state 0 or the spin up. Then you have the spin down for qubit 4, which is state 1. And what happens is that the states of these two qubits are flipping around, simulating the dynamics of the antiferromagnetic model when applied to two spins. And of course, here is a link that you can also see for yourself all the circuits that I had run on Starmon 5, along with the analysis as well. And what is the importance of simulating such systems? Of course, two spins is not a great achievement solving it with a quantum computer because you can very easily solve this system on your laptop right now. But the power of that comes in that if you think to yourself, okay, I have one atom and I put it on a fixed position in the crystal lattice, in how many states does my system have? And that is that the spin is either up or either down, so then I have two distinct states for the system. Now, if I have two atoms on a crystal lattice, then how many states do I have? I have either both of them are spin up, both of them spin down, or with opposite spins, so then that gives me 4 states for the system. If I go on with this logic, then 3 atoms on a crystal lattice gives me 8 states, and finally, for n atoms on a crystal lattice, I'm getting 2 to the power of n states. So this system increases exponentially. The size of the system increases exponentially. And that's a problem because then the computers, the classical computers that we're using are going to have a very difficult time as you add more and more atoms into that system. While, as you saw in my previous example, the mapping of the spins to the qubits is 101. So then if I have 50 spins that I want to simulate, I can use 50 qubits. And that's a very big advantage of the quantum computer. And so when we simulate quantum systems, what we're interested at is, okay, with the size of the system, how much does my number of qubits increase? And how many more qubits do I need when the system size increases? And also, what about the runtime? Because I showed to you, I break down the operations and I have unitary operations, but these, as Vivek also covered, these need to be transpiled into operations that our system understands. So then that breaks down into more operations. So then that costs more runtime, and therefore noise takes over after a while. So of course, what we're interested at when we're talking about quantum advantage here is really having a polynomial increase of the number of qubits and the runtime as the problem size increases. But enough for using the processor as a computational tool. Now I want to also show to you how we can use a processor as a sensor, because in reality, you're dealing with a system that is very sensitive system. As Vivek also covered, qubits have a T1, they have a coherence time, and that makes them very sensitive to their environment. But that we can use to our advantage. And how can we do that? For example, this is one example. And we will talk about cosmic ray showers now. So when you have cosmic ray showers, the cosmic rays that come from outer space, they interact with the upper layers of our atmosphere, and they create. There's a lot of products of ionizing radiation that go down, and if a particular ionizing radiation comes to our lab, let's say either gamma radiation or muon particles, then they pass through our dilution refrigerator, and they can hit the chip that we have inside. So normally this is catastrophic, because when you're running an algorithm, you want your system to be as much isolated as possible. And then it can happen that midway through your run, a cosmic ray scatters, there's ionizing radiation, and that radiation hits the chip, and then all the qubits just relax. And then all information is erased from the system. And how does this happen in superconducting processors? Basically, the idea is that ionizing radiation hits the substrate of our devices, and then there's a creation of phonons that propagate through the substrate, and if those interact with the Cooper pairs that make the superconducting state of the qubit, they can break them, and then they can create quasi-particles. And when these quasi-particles tunnel through the Josephson junction of the qubits, then the qubits relax and they go to the ground state. It's very involved, and there's a lot of physics about it that I am kind of skimming through here. You don't really need to understand all the process that is happening on the physics level. You just need to know that if there is a qubit excitation and an ionizing radiation hits the chip, then all of the qubits are affected and they all lose their energy and they go to the ground state. How can we measure such events? So we have made a protocol that we actually were running on Starmon 5 and Starmon 7, and that consists of having all our qubits initialized at the 0 state and then exciting them, and then waiting for a time of 2 microseconds until we measure. Normally, if you excite your qubits and the coherence time, the relaxation time, the T1, is about, let's say, 25 microseconds, then 2 microseconds of wait time is not really going to affect much your qubits. But in the case that the processor is struck by ionizing radiation, the T1 temporarily is reduced by a lot, almost to a microsecond and maybe even less than that. So 2 microseconds is more than enough time for the qubits to relax if there is such an event. And then we measure, we wait for some time, and then we repeat again. We again flip the qubits, and we measure again. And so 2 consecutive zero outcomes here are defined as a qubit error. Because think about it, if I have my zeros at the ground state and then I excite them and nothing happens because there's no ionizing radiation, I measure them in the 1 state. And then I just wait some time, then I flip the qubits back. If they have relaxed in the 0 state, they're going back to the first excited state. If they have not relaxed, then they go to the ground state, and then I excite them again and I measure. So in normal circumstances with no errors, I will always either be measuring 1, 0, 1, 0, or sometimes 1, 1, 0, 1, but I will not be measuring 2 consecutive rounds, all the qubits in the 0. So that's what we have as an error. And we define an error event when all qubits have that error in the same measurement round. And then we analyze those events, and we keep the events that we believe come from the effects of ionizing radiation that have a distinct recovery time. So these are the events that we believe comes from the impact of ionizing radiation, while some of the events that don't have a recovery time are just spurious errors that can happen. There's some kind of probability that all your qubits are going to be measured in the 0 state. That's just an error. And therefore, we reject such events. And we have studied, of course, the recovery time of these events. So here is the average. If we take all these events and we average them, we find the recovery time that is distinct for its device. So for Starmon 5, the recovery time is about a millisecond or so. And for Starmon 7 is about 250 microseconds. And here I'm also having the cumulative sum of the events that happen during the elapsed measurement time. What does that mean? I mean, the radiation background is constant. It doesn't change. So you expect that the rate is similar. I do not expect to get double the events tomorrow rather than today. The cosmic background is pretty much constant. So the cumulative sum is just a straight line. And what does this mean, the recovery time? It means that basically, if your processor is being struck, let's say Starmon 5 is being struck by ionizing radiation, then about a millisecond, most of the qubits are going to be corrupted. Also, okay, you might ask yourself, how can we be sure that this is truly caused by ionizing radiation? And for this, yeah, here I'm also showing the rejected, the average events of the rejected. And the thing is that we also used the lead shield. So we went to both fridges of Starmon 5 and Starmon 7, and we covered them with about a centimeter thick lead shield. And we saw that the events that we were measuring were reduced by an amount of 20% in both cases. And also we swapped the chips between the 2 fridges, and we saw that the recovery times as well as the rate of events that we were seeing were being kept constant. Here I'm going to show to you finally a movie from a similar experiment that was being run at a different time on our 17-qubit superconducting quantum processor, which is a Surface 17. And this data was given to us by an older member of our group. And here you can see the time where the event happens. So when all the qubits are flashing, you can see when the chip was being struck by radiation. And they slowly then recover. And it takes about the same time. It takes about 400 or so microseconds for all the qubits to relax back to the state that they were before. With that, I would like to finish this presentation. So I guess there might be a lot of questions because I covered a lot of advanced topics, and also detecting ionizing radiation bursts is a topic of our current research. So I don't expect everything to be well understood, but I will try my best to answer all of your questions. So thank you. In general, is there a good explanation what makes a measurement compared to the unitary time evolution? Well, first of all, a measurement is is non-reversible. Obviously, the unitary gates are unitaries. They can be reversible. Measurement. I mean, at the end of the day, it's difficult to really tell what actually happens because I don't think we know what exactly happens and why does the state of the qubit at some point decide to be measured at 0 and some other times at 1. But apart from this, that I cannot really give an answer. In the measurement, we send signals to the processor. And that's how we infer the state of the qubit, if I may so in a simpler sense. Is a calibration is a calibration is set according to such error rate occurrence. You mean the calibration of the device or so? I guess if I may, if I understand the question correctly, if we take into account the rate of occurrences of ionizing radiation when we calibrate the device, if we take this into account, that's what I understand from the question. If that's the question, then the answer is, the answer is no, because we cannot really do much about it. Ionizing radiation is always going to be there. There's a rate that events happen every, let's say, one event can happen every 60 seconds, one event can happen every 200 seconds or so. There's not really a prediction. It's a stochastic process. I cannot predict that in the following 60 seconds, I'm for sure there's going to be an event happening. We cannot take it into account. What we advise is that generally your algorithms should not exceed the relaxation time of your qubits, because then you're just going to get noise as an output of your algorithm, and that usually is lower than the rate of these events. So basically, we're talking about 25 microseconds on average, the T1 of your qubits. Your algorithm should be over by that time. So if at any run there's an occurrence happening, then you can just discard it in the analysis and not take it into account. Oh, so that means a maximum number of instruction. We don't impose such. The user is free to make as long circuits as they want. But they're generally advised for the runtime of their algorithm to not be comparable to the relaxation time of the qubits. Because then you're just gonna get noise.
Sorry. So for these questions, you mean that we should? Do you have some guidelines we should follow? For example, according to the complexity of the circuits, if we can exceed 10 instruction or so?
Well, there's no. So, I mean, that's a good question, because if you design an algorithm and you have that in mind, the relaxation time of the qubits in your device, then you're doing basically near-term implementations or so. You're making an algorithm that takes into account the device, and that's always preferable. I mean, basically a rule of thumb is that, like your operations, the total amount of your operations should not be in the microsecond regime if your T2s of the device and the T1s are also in the microseconds. because you should expect that if I leave my qubit, if I initialize it at the 1 state and I wait for 120 microseconds, so the T1 is 20 microseconds, I'm most probably going to find it at the 0 state after 120 microseconds. So you definitely don't want an algorithm that in total is going to take, let's say, 120 microseconds, because all your qubits will just have relaxed at the end of it. And you will measure nothing. Even though you may run it on a simulator that doesn't take into account noise, and you may get a result, you're not going to get a result when you run into STARMOD 7. So I guess once you start approaching runtimes in the microsecond scale, then you need to be careful. Like if your algorithm is, let's say, 1 microsecond, maybe you're going to be okay, depending on what you're doing, because also what kind of operations are you doing? Are you doing mostly single qubit gate operations? Because 2 qubit gate operations have much more error. So then maybe you're doing 10 2 qubit gate operations, and that would be 600 nanoseconds of runtime. Okay. And maybe then you're doing 30 single qubit gate operations, same runtime to our device. Then, you know, the 10 2 qubit gate operations are just going to give you a worse result. It kind of really depends on what you're running and what you expect to get as a result. But it's a bit trial and error in a way. But that's a very good question. Could you run Sol's algorithm for N15 on STARMOD 7? I mean, you can try. You can always try. If you have the connectivity that you need and you have the qubits that you need, you can always try. But it's a very involved algorithm. There's a lot of operations, and we run into the same problem, that if the total runtime is going to be long as compared to coherence times of the qubits, then you're not going to get good results. But you can always give it a try. I think then we're okay. I don't see any more questions. So then, well, thank you. Thank you. Very nice questions. Thank you.
Thanks, Marius. Yeah, thanks everyone. That brings us to the end of the workshop. I hope you enjoyed it and learned a lot. Please feel encouraged to start playing it and write your own algorithm and your own exercises on Quantum Inspire. You can use both the simulator, emulator, or even the hardware. We did use mostly STARMOD 7 at this moment, and the emulator. We started very simple. We went to more advanced, taking you over using the SDK and some examples there with Vivek, and a very advanced example with Marius, how a quantum computer can be used in some practical use cases. So thanks again very much. Please fill in the evaluation survey. I put the barcode link here. Please use it. That helps us improving these workshops and courses in the future. Yeah, if you have any further questions, there's always ways to find us, of course. And please enjoy your further exercises on Quantum Inspire and playing with Quantum Inspire. And thank you very much.